Hello, hello. Hello, hello. Hello, hello. Hello, hello. Almost there. Hello, hello. Hello. Okay. Hello, hello. Okay, okay. Okay, 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 okay. So, oh my God. Okay. All right, we are almost there. We're almost there. Okay. Oh, yeah. Hello. Hello. Okay. Okay. I think we are okay. Now, all right. Hello. Hello. Long time no talk. Oh, there's a chat. Oh, good afternoon. I love it. All right. I love it. Okay. Um, yes. All right. Great. Yes. So I'm going to gather from that you can. I'm going to gather that if you couldn't hear me right now, that you would tell me. I'm going to gather that if you couldn't see me, you would tell me. I'm going to gather that that you can see the crazy looking board from where we left off last time. I'm still fiddling with the ratio of board space to face space on this thing, and I don't know quite how it comes out in the recordings. Blah blah blah. We are recording. Blah blah blah. So we're now. You heard nothing from me all weekend. It was a long week. That is to say, you did not get something back from me, even if you turned it in, and you did not. There was not a new assignment or anything, for good or for bad, and we're not behind. But there was not. But if you've done assignment 1, you are definitely not behind. I'm behind you to get it to you. We're going to continue going over it right now. It does, like I sort of warned you, assignment 1 builds the whole thing that we have to study for a while. So it always takes a little while to get through assignment 1, and then things will roll. You will get more work, obviously, than you did this weekend. And it's still also the case if you get really, so we're about to dive back into going over this thing on the spring. And I'm going to let you know exactly when I think it transitions from being technically review to super new stuff. And then after we do it fully, I'll tell you why we're doing it and all that. But if it happens that, you know, you're really itching, like all weekend you'd already done this and you thought it wasn't hard or whatever, and you're itching for more and itching for more, you feel, if you're worried about the material not going fast enough, again, let me just, you can always look ahead in the YouTube lectures that follow this from last. I would have no problem if anybody did that, excuse me. And I will start asking you to do that for real soon. But anyway, in other words, what we're about to do probably was done exactly this way last semester in the summer, and you probably could watch if you prefer to do it that way. But we are going to continue going over this assignment 1, like one more, as soon as now everybody is admitted from the waiting room. I still don't even know if it's worth what the waiting room really does, but I do know that the Google Classroom code on the waiting room is wrong. I hope that hasn't affected anybody here. But all right, enough. I hope everybody had a good weekend. But yes, as the board indicates, we're in the middle of thing on a spring, assignment 1. We're going over it. The very last thing we did was a conservation of energy approach to answering a question. The very next question we're going to do is a very similar type of question. In fact, it is the same type of question with just the known and the unknown being flipped. So if you do the exact same method and do it properly, it's not a big stretch, but it is very easy and tempting to do the wrong, to not realize what we had done in the last. Anyway, this next question is to force us to really understand what happened in the last question. So I'll stop talking about it. I'm just going to do it. But you'll remind me. So I believe that the very next question that we are, okay, that's another. The very next part of the problem that we're solving, I believe is, and I don't remember what, someone will have to remind me what number question is, but I believe the very next question that we have to ask ourselves is, at what position will we find the mass, where will we find the mass when it has an instantaneous speed of exactly 3 meters per second? I believe that, or it might be 1 meter, but that's the question, right? Let me see if someone just put in the chat. They give us the speed, and they're asking us to find the location. And the speed they give us, I believe, is 3 meters per second. But does someone want to confirm that, just so we all know we're together? So I don't think I'm, but that's a yes. Okay, great, thank you. And could you actually tell me what's the number of the question? Is it like question 4A or what? Just so I can.
Question 5.
Great, thank you very much. All right. So question 5. So we're saying, right. So I believe this is a question, and I'm trying to rephrase in the most direct way possible. We're finding X such for the moment when the instantaneous speed is 3 meters per second. Like, the last question was to determine the speed when X equals 0, right? So it is the same question, just flipping what the knowns and the unknowns are. I say, I say this is conservation of energy again. So the way I write conservation of energy is like this. I say the total mechanical energy at any one particular position, like A and B stand for positions. When I do energy this way, A and B stand for positions, and A is and B is and of course, I could flip it around. You can make B the known and A the unknown, whatever, doesn't make any difference. But when I say unknown X, I mean an X for which we know the V. So I'm going to make that decision right now. But this is the way energy is always, the speed at one spot. What's the speed at another spot? It's always a speed spot trade-off. What spots do we know the speed? Well, actually, at this point, there's 2, right? We know we were originally given that we were originally given this, i.e. at X equals 0.15, V equals 0, right? There's one spot that from the start, we've known what the speed is there. We also just figured out in the last question, we also know that when X equals 0, right, which is not the same thing as X sub 0, but we also know that when X equals 0, V equals 3, approximately 3.87, or it might have been 7.8. Someone might have to correct me. I think, is it 3.78 or 3.87? But it's like the square root of 87. Thank you very much. Okay, so there's actually 2 positions that we know the speed. We could choose either one, right? We are looking for an unknown. We're looking for the unknown position at which the speed is some given 3. And hopefully all these questions are trying to help us put together a picture of the whole situation. That is, I'm now picturing an object that started from rest out here and was released. So it started speeding up and speeding up and speeding up and speeding up until it reached equilibrium and achieved a maximum speed of 3.87, right? And presumably it's going to keep going from there. It is going to keep going from there because it still has speed. But I'm not worried about that for the moment. I just know that it's sped up from 0 to 3.87 progressively. And I'm looking for a spot at which the speed had attained a value of 3. So I'm looking for a spot somewhere in between the 0.15 and the 0. Like, I'm just trying to say that these numbers hopefully are falling together in a way that making sense. Like if I were taking an exam, I don't know for a fact that I'm right, but I know so far that I have good reason to remain calm and happy because my numbers are not contradicting each other. Anyway, I can now pick whatever I consider to be a known. I'll pick the original known as known because just in case I made a mistake in what I solved for the equilibrium position. In other words, I'm going to say, fine, the total energy at x equals 0.15 must equal the total energy at the x that I'm looking for. You know, I'm calling it spot B, but the unknown x. Okay, so the total amount of kinetic plus potential, it must be a constant. So the total, like that's what total mechanical energy means, the sum of kinetic and potential. All of that sum at x equals 0.15 must be the same. I know I'm just dragging this out again, but it's been like 5 days since we've all seen each other. So here we are. For at that x that I'm looking for, technically I'm calling it x equals b because I have two positions A and B, but whatever, the x that I'm looking for, x. Okay, kinetic is always, well, actually, even before I fill that in, let me, even before I fill that in, kinetic energy comes from speed or motion, potential energy comes from orientation, place, right? Wait, do I want to, well, what I want to say right now is I know that at x equals 0.15, I know the kinetic energy was 0, right? Maybe I know that, I'm saying I know that even before I write out any more formulas or equations, like x equals 0.15 is the place where the mass was held still. By definition, it was a first spot. So there was no kinetic energy there. That's already a simplification I can make. That's nice. And I made something like it in the last part. However, looking at such simplifications, let me look to the right side and say, okay, at the spot I'm looking for, x, the position I'm solving for, will there be kinetic energy, I'm asking myself, and the answer is yes, it will be moving at the spot that I'm looking for. How do I know? 2 reasons. One, it's not moving at the other spot, and it can't be not moving twice. It would be not moving at all then. But second of all, I'm looking for the spot where the thing has a speed of 3. Like that's the given of the problem. So clearly it has a speed at the spot I'm looking for. So there is kinetic energy wherever whatever I'm looking for. Is there potential energy at that spot? So like I just asked myself this question. Now I'm asking myself this question. And I'm trying to ask it in English before I even put the letters down because I'm trying to get a picture of this. But so I'm asking myself, is there going to be potential energy at the spot I'm looking for? Well, the spot I'm looking for is not the equilibrium position. We've already identified the equilibrium position. I'm looking for some other spot. And the equilibrium position is the only place where there's no potential energy due to a spring. So all of this is to say that even before I start, and this is why I want to be careful, I want to say that right now my equation looks like this. Even if I don't exactly remember how to solve for kinetic or potential or something, I'm saying that now I have potential somewhere equals the sum of kinetic and potential somewhere else. Like that is not what I had in the last part of in the question from last Wednesday. There, a term on both sides had a term that crossed off to 0. Here, that doesn't happen. And I'm trying to drum that in because it's like so common for people to want to believe that you just set potential energy equal to kinetic energy. And that's frequently not the case. All right, so I have this. Now I can start filling in, like potential energy due to a spring is always 1/2 kx squared, okay? And again, maybe it would have been happier for some of us if I'd filled this in a step ago, but, and also, you know, assuming you already did this, and even if you did it right, I'm hoping you're writing down my way too, just so you know, if you already know that you already did it and you already know you did it right, you can actually relax and hear a different way, perhaps. Anyway, the other side is 1/2 mv, like kinetic energy is always 1/2 mv squared. I mean, always, you can memorize that in this class of physics, and it's true. Potential energy, we just said, is 1/2 kx squared. Here too is where I'm trying to say that maybe my method of thinking through the problem might ultimately help people in that if you just rush the algebra and stuff and aren't really thinking about it, it looks like I have 1/2 kx squared on both sides. I mean, I do. I have the term 1/2 kx squared on both sides. If one is not careful or one proceeds in the wrong order, you might think you could cross it off both sides because it is written on both sides. But it's 2 different x's, right? On the left, by x, I mean x equals 0.15. And on the right, I mean whatever x I'm actually solving for. You know, technically, in other words, the left side is like x sub a and the right side is x sub b, or however you want to write it. Okay, so I can't just cross it off. But what am I looking for? I am looking for that x be on the right side. So I'll subtract kinetic from both sides. Okay, kind of dragging it out, I know. So now I have this. Well, So I subtracted the 1/2 mv squared from both sides. I have a 1/2 kx squared, but this x is the x I'm looking for. Again, to be clear, technically that left one is, the one on the left side is x sub a, the one on the right side is technically x sub b. And again, I like to put in the numbers on the last step because everything until the numbers is physics. The numbers are just math. And so, there's a million ways to do physics right and a million ways to do important physics before you even get to the math. Anyway, I certainly can divide both sides by 1/2. I can divide both sides by 1/2 because I can factor out the 1/2. This also often, I know this is one of those things that you either totally find this boring or you find this confusing. Like when you can, I'm saying since I can factor out the 1/2, since I can factor out the 1/2 from the left side, then that means I can divide both sides by that 1/2 like I'm doing right now. In other words, if I didn't have the 1/2 on that, if it just one of those three terms didn't have the 1/2, then I could not cancel it out like this. But since they all had it, I can. Okay, and oops, sorry. And still, these are two different x's. It's x sub a and x sub b. And again, x sub b is the one I'm solving for. The one we're solving for. Okay, and the x sub a, again, is some known x, which I've decided is the 0.15x. All of this works perfectly if you could use the known x as x sub 0. As x equals 0, but then you just have to plug in the corresponding the corresponding v. But okay, so we have this. So we're just about ready to be able to plug in numbers. I'm just going to do one last. I'm looking for x, so I'm just like isolating the x. K, it is the same k. It is the same k. And again, I'm saying this, some people, it is the same k, but I cannot cross out the k's. Like this is exactly the opposite case of algebra from what we had 3 lines ago. I now have x sub b equals the square root of blah, 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 blah. I've got an x in one term of the numerator, I've got a k in one term of the numerator. I've got a k in the denominator, but because I don't have that k in the mv squared term, I can't factor it out from the top. So I can't just easily divide the top and bottom by k. Like it does not cancel out, just to be clear. But I certainly can plug in numbers now, and that's the last thing I'm doing. We'll be done with this. I'm not saying it's terribly interesting, but so I'm going to go to the next page just to recopy that. Like what we have now is this. I think this is, I'll just check again. The k is under the whole thing. I'm just checking. Yeah. Okay, and so then, and I will pause obviously when it, but k the whole time is 200. I should put in the units. I'm not going to because I'm going to run out of room. The x that I'm talking about here, the way I did it, the x is 0.15. There's a way to do it where your x is 0, which would sound like it would make things easier, but then you have to put in a different v. So like your numbers will be different if you do it a different way, but your final answer will be the same. The x I'm putting in is 0.15 squared minus 0.3. The v that we're putting in is the 3 that they asked about, squared all over 200. And I believe, and someone should check, I believe that if you punch those numbers into your calculator, you get approximately, I don't know why I changed the colors in the middle, sorry. But I think I mentioned this last time. I believe that the answer you get is 0.095. I'm rounding, of course. And if we're an exam and you got 0.094 or 93 or whatever, I'm sure that's a rounding thing and that's no issue. But I do want people to check. Like I am obviously saying this from memory, so I could be making a mistake, but I believe that is the answer. But what I want to really make clear is if you got an answer that looks something like 0.116 or 0.113 or 0.11 something, then I do want to stress that that's not a rounding thing. Like that I would count as wrong on the exam. That's the most common wrong answer, and I would look for it type of thing. Because if you got that answer, it means you actually did set up the physics wrong and you're actually is a physics mistake. So and someone in the room must have made, there should be no embarrassment in making that mistake. I want you to see that. So if anybody wants to raise their hand about it, please do. Like I'll explain it. But first, just to confirm, I believe this is the correct answer. Can I get any confirmation or denial or question or something, or chat, or are we alive? Oh, good afternoon. Okay. Oh, and I didn't even see the gallery. Hello, or can I get a thumbs up if we agree or something? Wow, rough times. Wait, you can hear me though, yes?
Wait, I have a
Oh,
question.
oh, good. Okay, yes,
Okay,
please.
so from physics 1, I learned that like for some problems, if it has like a square root thing, you have to put plus minus.
Oh, that's a really good point. Okay. Wait, let me address it. One thing, are you okay with the actual number itself? Like, did you get the same number?
Yeah, I got 0.09.
Okay, cool. So now as a plus minus, excellent point. Strictly speaking, I should put plus minus here, but here's where, well, let me see. It really totally depends if we're going to be that, and we should be that careful. You're absolutely right. But it 100% depends on exactly what the question asked. So I don't know do you have the question in front of you?
Yeah, I do.
Okay, can you tell me, or can you just, could you actually read it out? And I'm not trying to put you on the spot, but I want to it does depend on exactly how the question said. So could you read it out loud?
Okay, in meters, at what position does the mass achieve an instantaneous speed of 3 meters per second?
Okay, all right, great. So then I totally agree with you, and I think this is a great point. And you are Casey, yes? Are you
Yeah.
Casey? Okay, so what Casey's saying is, right. Like, I'm looking for a square root here, and unless when in general, if I don't know anything else, she is right to say from physics, and I don't remember if by physics 1 you mean here at John or somewhere else, but yes, I agree that a square root, we should at least at first look at always the positive and negative value of a square root. We at least should look at them both and then maybe ask ourselves, do they both apply here? So first of all, I agree with Casey that strictly speaking, if nothing else is in our mind, or if it's an exam, we should start with the instinct of checking all possible values. So yeah, putting the plus and minus. Now what I do though is then, maybe I should include this as a written step, or I do it in my mind. I do agree that the square root of all that stuff is going to be either the positive value 0.095 or the negative value. Like, they both satisfy the math. So then I ask myself, do both answers actually satisfy the physics question, which is where it comes to the close reading. Casey read the question and it said, at what position does the mass achieve an instantaneous speed of 3 meters per second? That means it could have a speed going in one direction of 3, or as far as the question is asking, we are also accounting for any moment that the mass might have that same speed of 3, but be zooming in the other direction, i.e. be on the other side, coming in from the other side. Therefore, because the question said speed, I totally agree with Casey. I mean, I know it's taking a long time for me to say that, but I absolutely agree with Casey that I should say plus or minus. I think she's right. And just to stress to everybody, if the question had said velocity, then if it said when does it have a velocity of 3, then I'm not sure that I would put the plus or minus. Then I probably would just include one value. But yeah, okay, I'm taking too long. But yeah, great point. And that is the answer. Anybody else? Was that the? One second, I'm just getting another chat. Yeah, but that's good. I'll go and say. Okay, if there are no other questions now, I'll move on to the next one. And all right, I'll move to the next one. One thing to again compliment everybody or reinforce, again, I don't believe that there's no such thing as stupid questions. Like, I do think, and I think can be obnoxious questions. There can be stupid questions. I haven't heard one yet for this class, either this semester or last semester. And I would say, like, the one thing that sometimes people think is a stupid question, like, it's true if something has been asked 3 times already, and then someone hasn't been paying attention at all and asks the same thing for the 4th time. Okay, that could be annoying to everybody and kind of almost bordering on rude, even if they don't know it, right? And no one wants to be that person. But again, no one's done that at all in this class. But 2, it occurred to me this weekend, like, I think one of the reasons I love this public chat business is, as long as you can frame your question in a way that you're comfortable with putting in the public chat, not only will I get to it better than an email or something, I promise I will get to public chat, but also if you put your question in the chat, then if someone does zone out for a while, they can always I guess you guys already know this, but I hadn't thought of this, that you can always just quickly scan the chat to make sure that your question hasn't been asked before 3 times. And as long as your question hasn't been asked 3 times, I can almost assuredly say it's not a stupid question. So just to remind everybody, like if you don't see the question in the chat, even if you think I answered it 2 days ago, I'm sure someone else needs me to answer it again. So blah, blah, blah. All right, so anyway, that was a great question. Oh, and I'm gonna look in the chat, okay. Oh, okay, got it, okay. So I'm gonna move on though. The next, now we intersperse some English weirdo questions here for a little bit before we get back to the heavy mathematics. So I don't remember which, I think the next question is how many, someone please tell me, but I think the next one is how many times does this thing go back and forth before it slows down? Or could someone just tell me the next question, please?
It's hard. How far will the mass compress the spring?
Oh, okay, great, thank you. Sorry, thank you. And I totally appreciate that you are that guy that says that thing when I need that thing. All right, so how far does it go on the other side? This, if anybody, I'll try not to drag it out. It's exactly what everybody thinks, I think. If you think about this question at all, if you have any guess in your mind, your guess is right. It goes to 0.15 on the other side. I guess this is question 6. Yeah, I mean, the fast answer is absolutely negative 0.15. And can you just say that and write a sentence of English or something? Like, if this were an exam, do you have to prove it? Here's the proof. Like the thing that we've been saying for the last 2 problems, that energy is conserved, we've been using it already. However we justified it, we justified it in the last 2 parts. If we believe that energy is conserved, it really does mean, and we don't, I'm saying you don't have to do this all out again, but understand what it means. If we're believing this business that we're using, then that means the next time the mass has a V of 0, it has to have the same X as it had the last time the V was 0. I mean, it's always a speed spot trade-off, just like with gravity, a speed spot trade-off. So the original place the mass was at rest was at 0.15. So when it had that much, when it had 0 kinetic energy originally, it had all potential energy, it had a certain amount, that total amount of energy can never change. So the next time all of its energy is potential again is its next maximum displacement on the other side. And the next time all of its energy is potential again, then its potential energy will be that same number. I guess all I'm trying to say here is if we've believed energy was conserved in the last 2, we got to keep believing it now. This does assume there's minimal friction acting on the system, but okay, that's fine, that can happen. So yeah, so this is the answer, just like you'd expect. And then it also follows from that, I think maybe this is the next question. Then it asks like how many, and please correct me if I'm wrong, but I think after that asks how many trips will this thing make before it comes to rest. It's not meant to be a trick question. It's almost obnoxiously phrased. But I mean, but if this is indeed a next question, the answer is infinity, right? This thing will go back and forth forever without damping, without having the amplitude of its swings get shorter and shorter. It will do that if indeed energy is conserved. Now, of course, this is where physics starts looking like Smurf Village to a lot of people. Like, I am now saying that this mass on this spring that we are analyzing will go back and forth forever. Of course, that means we're analyzing an ideal spring, not an overly realistic one, perhaps you might say. And that is true. But I think the thing to stress again is just because this shouldn't be any harder to believe or harder to picture than even the first question that we answered. Like if you believe that the mass really is 3.87 when the thing gets to the center, then you have to believe this is going to go on functionally infinitely. Is there any spring in the world that actually has no friction acting on it? No, but, and here's the key that I'll try to say over and over, I always try to say is to convince everybody of physics and stuff, especially in this course where we get, well, anyway, is there a mass in the world that's on a spring in the world where no friction's acting on at all? Absolutely not. No, of course not. However, is there a mass in the world acting on a spring where the friction, where in order to measure the amount of friction, we would need measuring equipment that is so delicate and small that any measurement that we would make of the friction would not register. I'm not saying this properly at all. What I'm trying to say is what there definitely are in the real world all over the place, and this is why we study all this stuff, is there definitely are systems where the frictional effects are so much lower than the output effects, the thing that you're measuring, that you literally can't measure both effects on the same equipment. In other words, there definitely are systems where the slowing down effects would read 0 on any measuring equipment that you're using to measure the displacement effects or the velocity effects. I'm still not making sense. I'm going to go on in a second. I'm saying the only way to study a realistic spring is just first by studying an ideal one and then adding details one by one as you go. And that's what we're doing right now. I'm going to keep going. But the answer is infinity to that. Then I think the next question, I'm probably doing them out of order, but this is where we get back to actually analyzing the situation. I believe the next question is, it says, let's just picture the first section of the motion. Let's just picture the mass going from its initial spot to the equilibrium spot. Like, even though I hope we all know at this point that when the mass gets to the equilibrium spot, it's going to keep going, right? It's not going to stop at equilibrium. That's not what equilibrium means, right? I think we said this last time, but we're assuming that the mass is going to be speeding up toward equilibrium and then keep going. But we're right now just going to analyze that first chunk of the motion. We're going to ask ourselves whether certain quantity magnitudes, certain measurement magnitudes are increasing, decreasing, or remaining the same as it goes. Again, I hope I'm on the correct question here, but in this sheet, it asks about speed, acceleration, and then the derivative of acceleration, which is called jerk. I'm going to back up for a second. So I'm looking like I'm off sheet here for a moment. Even before I literally answer speed or velocity, magnitude, acceleration, and jerk, I'm going to back up 1 second and look at position, even if the sheet didn't ask that, just so I can make this point super clear. In other words, I'm going to say now, okay, from x naught, from x equals x naught, which equals 0.1, from here to x equals 0. Does the following magnitude increase, decrease, or stay constant? Okay, I know this is illegible. This is the question I'm about to ask. I mean, I think it's the next question on the sheet. I'm going to look at a number of measurement magnitudes and ask whether they're increasing, decreasing, or staying the same just with regard to this first chunk of the whole motion. Okay, right? So to make this clear, I'm going to change it by another color. I'm starting with position. Again, I know explicitly speaking, I don't think it asks for this in the sheet. I'm not trying to confuse, but I think I wish it did. It should have. And I'm doing this so that the whole question really becomes clear. So position, does the position, go up or go down or remain the same? And I'm just going to say straight up, like the way we're defining things here, the position decreases. It goes from positive 0.15 down to 0, right? The way we have set up this coordinate system. And again, we could have set up others, but whichever one we set up, we're going to answer all these questions in a consistent manner. So I'm saying the magnitude of position, decreases. Then, and anyway, that's what the position does. Then as for what the sheet asks then magnitude of velocity, well, i.e. speed. Well, the speed is not going from, so this position went from 0.15 to 0. The speed, so now we're asking speed, the magnitude of velocity. The speed okay, that was that answer. The speed is going from speed 0 to speed 3.87, like at the equilibrium position we figured out, right? So the speed goes from 0 to 3.87, and we're again only asking about magnitudes right now. So the speed increases. Then it asks, oh, sorry. Okay, then it asks about the acceleration, asking about it for this, and I want to use the same definitions. Like I don't want to just like change my rules now that I'm asking this question, answering this question. So the acceleration now from that end point, as the thing is zooming in toward equilibrium, well, the acceleration went from something high. I don't even remember if we figured, oh, we did figure it out. Yeah, it went from like negative 100 meters per second squared to 0, right? Now, that 100 was technically a negative, technically it mattered in some context, blah, blah, blah. But right now, again, I'm asking about magnitude. So I don't want that to throw me off or confuse me. The magnitude of acceleration is going down. The magnitude of acceleration is going down from 100 to 0. So the acceleration is decreasing. Right, and then so let's just, now the final question is the one we maybe is really the punchline of this, but let's be clear then. I've got this object that's coming in. I'm just looking at the first fourth of a cycle of motion. Presumably my answers are going to be different for any other fourth, but presumably they'll follow a similar pattern. Just in this beginning part, I've got an object that's, so to speak, moving down while it's speeding up, while it's accelerating down, right? Like this thing is gaining speed. It's gaining speed. It is accelerating, but please note already we're saying while it accelerates, the rate of acceleration is decreasing. Now, and that can happen. And I'm not saying that's a contradiction, like, but I am saying it might jostle your brain when you say it out that way, or more likely, you might not have a problem with me saying it out that way, but just remember that in some part of your brain, whenever you hear that the speed is increasing and that this thing is accelerating, it's very easy for a lot of people to unconsciously then assume, the acceleration's increasing. Like people do, and we're trying to say here, no, let's be careful. It is increasing in speed, therefore it's accelerating, while its acceleration rate is going down. So we're building up speed at a lesser and lesser rate as we go toward the equilibrium. That's what I'm saying so far, right? And so then this next question, and by the way, and how I know is because I just put in the numbers. Like we knew all these numbers. So I just put in the first number at the beginning and the last number. So so we know because of all the work we've done up to this point in the sheet. So now the next question, we've never been asked before in physics. Like it's now asking, what about the derivative of acceleration, which you may or may not ever have thought about in your life. The derivative acceleration, which it does have a name in physics, it's called jerk. And that's, yes, jerk. It's not just your little brother anymore. This is the word for it because it sort of is what it feels like. So a change in acceleration is kind of like not just you changing your speed while you're driving your car, but maybe shifting a gear would be a dramatic example of it. What it really is, though, is the derivative of the derivative of the derivative of position, right? In other words, we're talking about this, right? The third derivative of position with respect to time. Now, a derivative is just a derivative, right? In principle, once we know about derivatives, we could think about a seventh derivative or an eighth derivative, like it's just one more rate of change. But I don't have any physics equations about this that I know of yet. Like we haven't calculated the jerk or anything. But to cut to the chase, let me just say that there does seem to be a pattern developing here, right? I mean, it does look like the position is going down while the speed is going up, while the acceleration is going down. If I had to guess, just based on this pattern, I'd certainly, a guess might be that the jerk must be going up. Is that a correct guess? By the way, it turns out, yes, it is actually. Does a guess prove anything? No, a guess by itself doesn't prove anything. But first of all, if that was your guess, I think if there was any guess to make at all, it's the most reasonable one because the pattern, I'm going to pause for a second because I see something in the chat. But I want to say more about that one second. Sorry, 1 second. Okay, and again, let me just say, so when I'm pausing occasionally, it's because something comes through the chat that's private. And so far, again, I think you guys are using the public-private thing exactly right. I appreciate it. I definitely do. Okay, so we're asking about the derivative. To get to it, the answer is, yeah, it's going to be increasing. If you guess that the pattern is going to keep holding, you're right. And there is reason to believe in this pattern. We're going to really prove this sort of mathematically a little bit later in the sheet, like a few more steps. But what I'm just trying to establish right here, one thing I know is not happening to the derivative of acceleration. Like we're now being asked, we're getting into new territory now. We're starting to conjecture. We don't have a formula to rely on with a question like this. But my 3 choices were increase, decrease, or stay the same. I have very good reason to believe that this thing is not staying the same, because what I'm seeing already is that nothing is staying the same, right? Like what's making this motion simple is that it's repetitive and easy to describe. It's something going back and forth the same way forever. What's making it simple is that it conserves energy. So it's going to repeat in a cyclical way. And as long as I understand what one cycle looks like, then I'll have the simplicity of being able to extrapolate that one cycle. But what's not easy about this is that we noticed very early in the problem already, acceleration's not constant, right? Acceleration's not constant. So a lot of our old physics, which is all based on acceleration and force and all these acceleration equations, we can't use a lot of our old physics because acceleration is changing every moment. Well, if acceleration is changing every moment, that means there's a change in acceleration. Like there definitely is a 4th derivative going on here, right? Like there is one. I don't know what it's doing, but there is one, because acceleration is not constant. Acceleration is, in other words, I'm saying so far. Oh, sorry. I don't mean that. Wait, that's not. Just to be clear, do you see that I'm saying, since this is just like any other derivative, since the velocity changes, then acceleration does not equal 0, right? Because acceleration is change in velocity. So since we have a changing velocity, we know we have a non-zero acceleration. Similarly, since we have a changing acceleration, we know we have a non-zero jerk. Like, right, that's what derivatives mean or are. Whatever I know about the pattern from one to the relationship of one derivative to the next follows to the next to the next. So let me take this one step further. Look what's happening. What everybody knows, if they're picturing a mass going back and forth on a spring, what everybody I think can picture in their mind is, for a while the mass is in positive positions, and then it gets to negative positions. Right? And then it gets back to positive positions, and then it gets back to negative positions. The positions keep crossing back and forth from positive to negative as the thing goes back and forth across 0. But how does that happen? How does the thing why does this thing change from positive positions to negative positions? Because it has a negative velocity, right? For something to go from positive places to negative places, it must have a negative velocity. How does it get from negative places to positive places? It must have a positive velocity, right? So this thing is not just going back and forth from positive places to negative places and back to positive places again. While it's flipping back and forth from one zone to the next, it's also flipping the direction of its velocity. It's traveling that way, and then it's traveling that way. Like, that's a different idea, right? First it's here, then it's there. First it's traveling this way, and it's traveling this way. like and um and what makes its velocity direction flip, what flips the velocity direction? An acceleration. If something has positive velocity, okay, I know I'm just talking now. This is but I think I'm just about done. But this is the tricky thing to explain. And if you remember a problem called Big Old Duck from Physics 1, if you happen to take Physics 1 at John Jay, and if you remember a problem called Big Old Duck, there was something going on in Big Old Duck that's exactly like here, and sort of why we do that problem then. And if you don't remember the problem, if you don't know the problem, don't worry about it. It just, the situation just was though that there was some duck. There was a duck traveling along in a certain direction, a positive direction, it had a velocity of like 20 meters per second, positive or something, but it had a negative acceleration, this duck. It was traveling positively and it had a negative acceleration. What we all came to realize back then in Physics 1, and again, anybody would follow this, whether you've ever seen this duck before or not, if something has a positive velocity, but a negative acceleration, what that necessarily means, if that goes on forever, what that necessarily means is that the thing is eventually going to get to velocity 0, but its negative acceleration will keep subtracting velocities from it. So it'll get below velocity 0 into negative velocities and come back around, right? If you have a conflict between your acceleration and your velocity, you will eventually change the direction of your velocity, right? Like something thrown up with positive velocities in a downward pointing gravitational field, if something's thrown up in negative acceleration, it eventually velocitizes negatively, right? So to switch your direction in a derivative, what you need is a higher derivative of the opposite direction. That's what I'm trying to say, that if this thing, if this mass on this spring had positive velocities, but eventually those velocities became negative and it turned around, that's because it had an acceleration that was negative. Okay, like if something goes from positive velocities to negative velocities, it must have a negative acceleration. But then this thing then flipped back to positive velocities. So at some point its acceleration must have flipped, right? Like acceleration is like a lever on velocity. If your velocity is going to flip, it's because your acceleration lever is pointing the other way. Okay, but then eventually it flipped again. So the acceleration lever must be flipping. The acceleration is flipping here, just like the velocity lever is flipping. So there must be a higher derivative that's flipping it. What I'm saying is a bit confusing and a bit English because I'm trying to establish a pattern. What I'm trying to say is once you realize, oh, we've got position flipping from positive to negative, that must be because of a velocity thing that's flipping from negative to positive. But if a velocity thing is flipping back and forth from negative to positive, there must be an acceleration thing that's flipping from negative to positive in order to turn the velocity. And if that's happening, there must be a jerk that's flipping it. In other words, what I'm really trying to establish in this long discussion is if whatever part of your brain can believe that a mass that conserves energy on a spring, whatever part of your brain can believe that it would go back and forth forever, going from positive places to negative places, like, and again, forever is a very long time, but just picture that it's a huge mass in spring that's got low enough friction that it's going to take 85 years before it damps out. And that's really the thing I was trying to say before. You don't have to picture perfection. You just have to picture something that's designed well enough to not run out of steam while you're paying attention. And that is very, very realistic and possible. So picture a mass. If you could picture a mass that's in a museum or something, or like the Foucault's pendulum in the what do you call it? In the national, oh my God, in the big museum in Washington, D.C. I'll think of it in a minute. But anyway, if you just picture some big mass on a spring that's just so big and so smooth and so like made in Tokyo that it's yeah, sure, it's slowing down, but so slowly that you have to live 100 years to see the damn thing die. Then if you're picturing that, then what I'm saying to add to the picture now mathematically, realize that as long as you can picture something flipping its positions back and forth for a long time, then actually, even in the simplest possible case of that, it must be flipping all of its derivatives, all of its derivatives all the time. In other words, I'm saying if velocity is going positive, sorry. If velocity is going positive, negative, positive, negative, positive, negative, then there must be an acceleration that's going negative, positive, negative, positive, negative, positive. And if that's true, there must be a jerk, a third derivative that's going positive, negative, positive, negative. And if that's true, there must be a derivative of that, which technically is called the whip, actually, like the fourth derivative. And that must be going negative, positive, negative, and then there must be. So now this is the first time we've ever seen this. This is why I'm making a big deal. Okay, I'm saying it in English, but what I'm saying here is this simple system, this energy conserver, right? Sure, we're picturing that it's a very, very good one. We're picturing that it's a spring that's like really long and really strong and really stiff. But whatever comes with that, whatever part of your brain can picture something going back and forth for a long time, please now add to that picture that at every single moment, therefore I'm saying at every single moment, therefore, at every single instant, i.e. point in time, right? And position, i.e. point in space, at every single point in time and every single point in space of this system's motion that we're analyzing now, I gotta learn to not keep, I know this is so annoying that I keep going on the side like this, but I'd rather do that than turn the page. The key point that I am trying to make right now that is, I think, interesting and should not make things harder. It actually makes things easier to deal with if we recognize this truth. But I'm saying now we're looking at a system for which at every single point in its motion, every single point in time, every single point in space, if we were to look at the rate of change of position with respect to time, right? If we're looking at how fast this thing is moving or how fast it's accelerating or how fast it's jerking, whatever we want to look at, we will find that every single point, there's an infinite number of derivatives that are taking place at that moment. Like no derivative just cancels off to zero. No rate of change is constant. This is a new thing for us in physics. Again, if I'm taking a while on it, I want you to realize why. Like when this is as opposed to free fall, like when something falls, we say its position is changing, so it has velocity. Its velocity is changing, so it has acceleration. But ever since the third lab of physics 1, if you took physics 1 at John Jay, ever since the free fall lab, the bolts on a spring lab, and I'm sure if you didn't take physics at John Jay, like wherever you took physics, somewhere early on, once you start looking at gravity near the surface of the earth, the whole purpose of gravity, the reason we all study it so much at the beginning of physics, gravity near the surface of the earth, I'm saying like free fall, is that there's a situation where we think there is an acceleration, but it's a constant acceleration. So the rate of its change is zero, like that. All the derivatives higher than number 2 cut off to be zero. And we only have to deal with derivative number 2. And we love that because F equals ma. So we do a lot of physics that we do in physics 1 is we're hanging out on derivative number 2 because that's where the action is. Here we are saying we're now going to look at a system where derivatives are running as high as you like at every single moment. No derivatives are zero. They're just all spiraling. So even though it's simple and predictable in a way, there's actually something complex and rich happening. Okay, I'm just saying that. So we've got infinitely differentiable motion here. That's what I wrote on the side. Infinitely differentiable. The rate of change of position with respect to time everywhere in this motion is infinitely differentiable. You've got derivatives as high as you like, and they're all gearing each other. Every higher derivative is gearing the lower derivative to flip. Blah blah blah. Now, what does this mean? It certainly means acceleration is not, like, certainly, to put it mildly, well, I guess I'm saying this, in sum, I'm saying, sorry, for a mass on a Hooke's law spring, point is that unlike free fall, for example, like for free fall, the third derivative equals 0. For this, no derivative equals 0. Okay, now who cares? Like, what does that do for us, or what does that mean? Well, it means now, if we get to the next question, and again, I may have done the question slightly out of order, and I apologize, but I think I'm now up to the very last question of the sheet, which really, which really is the meat of the whole thing. The next question, and everything else we've said thus far. So everything we're saying so far is a regular everyday mass on a spring, like this is what we expect based on the physics we know. We think, it seems, that if you put a mass on an ideal spring, which really means that it's very long and very uniform and very strong, so, and you let the mass just like move a little bit compared to how long the whole spring is, right? We feel that it's going to do this kind of symmetric motion. If it conserves energy, it's going to go back and forth, always between the same two spots. Oh, in some so far, in some. Okay, just again to sum, and what we're picturing is something will go back and forth, something. If you put a mass on a spring like this, it'll go back and forth between two endpoints. Those two endpoints, by the way, we usually call the amplitude points. I don't want to make this screen any, but please note that those two endpoints are usually called amplitude points. The thing will oscillate symmetrically, cyclically, periodically. I'm sorry, oscillate means go back and forth. So it'll move back and forth between these two endpoints forever, as far as we know. And each endpoint will be a place of maximum potential energy and minimum, i.e. 0, kinetic energy, whereas the equilibrium position that it's oscillating through will be a place of maximum kinetic energy and minimum potential energy, 0. And same thing can be said of whatever I'm saying of potential energy also applies to acceleration, whereas whatever I'm saying about kinetic energy applies to speed, right? I mean, not the numbers aren't the same, but wherever it has maximum acceleration, it will have maximum potential energy. And wherever it has maximum speed, it'll have maximum kinetic energy, et cetera, right? So then, I know all of this stuff, but then we finally ask this question, given this such a system, and we're gonna call this an oscillator, anything that goes back and forth like this cyclically, we call oscillation. And we're gonna now begin to develop a very specific kind of oscillation seen in this problem. But the very hello. Okay. Hi. All right. So I totally lost my internet just cut out right in the middle of, so I was saying, sorry, I don't know if, I think you're all back. So can you hear me? Can anybody hear me?
Yeah.
Yes. Okay. Thank you. All right. Sorry. So I was babbling too much anyway, but my thing dropped. What I want to say is, I want to get to this next question. Oh, and I see more and more pictures are coming. Thank you so much. Wow. Okay. Sorry. What I want to get to is, I'm sure what everybody wants me to get to. I want to get to my screen. I want to get to the question. The thing asks. Okay, there we go. The thing asks, where will the mass be at time equals 1 second? This is finally the question. It's taking me, like, I know, a week to even get there. But and correct me if I'm wrong, but I believe this final question, question 8 or 9, whatever it is, at t equals 1 sec. What is x, right? This is the last question. And let me now, I mean, believe me, I want to get to this as much as anybody does. Just note how simple sounding a question is. It's the most fair sounding question in the physics world. Like literally, you could not be more directly physics than to ask, at given some object at a certain time, what will its position be? Like that's literally always what physics is. Where will something be when, right? So it's completely fair to ask this. And it's, I think, hopefully completely clear what we're asking. We're like now have all these patterns established, and we want to know at the first moment, what's x? And if we, and let me add, all the other stuff that we're saying about this mass spring system, hopefully is to help us develop a picture so that we could straightforwardly, so that we could have an answer to a seemingly straightforward question like this. Like this is the central physics question to ask about any system, right? None of that, however, it's not easy to answer. It's going to generate some work, the general physics. Like, basically, I can't say that I understand a system or have scientific predictive model of a system unless I could, answer this about that system. So I want to be able to answer, okay? Normally the way I would dive in and answer a question like this, or like in physics 1, but again, the question is simply given t equals 1, what's x? So I'm sorry, sorry. Right now, there's nothing special about the first second, other than that it's, actually there's nothing at all fair about it. We do assume that this thing is going to go on forever. So presumably I could ask about any time I wanted. And if I could get the answer of where the thing is going to be at one time, I would be able to get it for any time. In other words, 1 second is just an example to make my thinking concrete. But what we're really looking for here, is x as a function of t. What we want, right? If this were in the middle of an exam, or if this were in fact in history and came up and confronted us as it did Sir Robert Hooke. I don't think he was a sir, but whatever. Of course, what would go through my mind is, do I have a formula? Do I have an equation? Like, okay, like the world is saying, assume that you know t, then solve for x. So anybody and everybody would be like, oh, can I use x equals 1/2 at squared or something, right? Like that's what we would have done in physics 1. We would say, oh, x equals 1/2 at squared. We plug in t, we get out x. And there's nothing wrong with that. It wasn't primitive thinking or false thinking. It's just, of course, it assumed that there was an a to plug in. And now we realize there's no a to plug in here as such. It's changing every moment, right? So I'm not going to say, I'm going to cross this. Very good. Like this, that I wrote it because it would be my first thought, as it might be yours. If you think that first, right, it is wrong, but it's the right first thing to think. This won't work because a is not a constant value. There is no one value of a to plug in, okay? So that won't work. In fact, no equation that involves an a will work. So I'm gonna have to think. Maybe then I would go try using energy, like we were doing in the first couple of questions. Like I might try something like this. Oops, sorry. And again, of course I know what is gonna work, but well, anyway, I might try something like this. Which is what we were just doing for when A started to fail us in the last couple of questions. But that also won't work. Now, I'm not saying it's wrong, right? Like the top thing is right, it just doesn't work. Similarly, this is right, but it doesn't work because it doesn't mention time at all. It won't, we're be asking a question now of what is a position given some certain time. This thing is a speed position relation. It won't inform us at all about time. In fact, it's independent of time. That's in fact why it's as powerful as it is. For what it does it really well, but it won't tell us anything about time. So what does it say? What we want, what I'm really looking for here. And this is what I want to start getting used to now, right? We're looking for a function. Like this is what, instead of, the question's asking for an answer. What we're used to in science, maybe even in physics, we're used to thinking, oh, what's the equation to plug in for getting this answer? And maybe we're even used to the fact that often things are complicated, so you have to do a lot of equations and a lot of steps. But at some level, a lot of us are used to, if I'm looking for an answer, I need to use an equation. When I'm trying, what we're gonna now start transitioning into here, and the labs are meant to do this too, we have to start thinking more like, no, we have to develop equations. The answers we're looking for in physics really aren't numbers. They are equations that we're looking for. What we're looking for is the generalized relations that we can use later for any and all particular numbers that might arise in the lab. So I just want to, so there is going to be an answer to this last question, and we may not get it today, and that is okay. But like, yes, the question is literally saying, what is the position when t equals 1? There is an answer to that. In fact, I believe the answer is 0.113 meters. I believe you can, or am I confusing with it? Or 0.116 meters. Someone could, I think, but I don't care. And the reason I can't even barely remember is what I'm really looking for is the equation that in the final moment, I'll plug in 1 for t and it'll pop out x. Once I really have that equation, then I've done the hard part and done the work, and that's what I'm looking for. But I'm saying all that also to make everybody realize this is not a question of just looking up the equation. Like that isn't the issue. The issue is we don't have it. We have to develop it. That's what we're about to do now. Okay, so and that's what physics does. So how can we? We're looking for an equation, x as a function of t. And I'm literally looking for a situation where t will be the independent variable, like the input. And I am dragging this out because we're about to get mathy. I'm not trying, but once it gets mathy, it gets really mathy, and I really want there to be a foundation for that math. So I appreciate everybody's patience, but t is the independent variable, x will be the dependent variable. I'm looking for some relation between the two. Like an example certainly is x equals 1/2 at squared plus v naught t. Like that would be an example of a function, and of the type that I'm looking for. Plug in a t, you get out an x. Everything else in there are constant values, right? When that equation works. But that's just not the answer here because it won't work here. But I'm looking for something that looks like that. X equals blah, blah, blah of t. Okay, how can I possibly do that? I have to write down whatever physics I know. Like what, okay, so we don't know. And here's where, again, there's an answer to this, and someone could look it up on the internet or already has, and I could write down that answer. I know it too, but I'm trying to show you why it's fair to expect us to get that answer. Like, I don't want that just to be black magic. Like, where did that answer come from? So that's what we're developing here. We don't know x equals, we don't know the function. We're looking for that, but we do know. What we do know is what we're going to write down, of course. What we do know, we know we have a mass on an ideal spring. So we know this, right? We're looking for equations, right? In fact, we're looking for an equation that relates x to t. Well, one equation we do know that has an x in it is Hooke's law. That is a given for this problem. Also, it's a physics problem. Like, we know something specific about the force of this physics problem, and we know how forces in general work in physics. We know this. Okay, and technically these are both vector equations, but we know that, like, or you could write F net equals ma, but we know the sum of all the forces on something equals ma. Yes, by the way, we also know some numbers here. Like, we know x naught equals 0.115 or 0.15 meters. I don't care. I don't consider that a known. Again, trying to get in the habit, you're going to see we have fewer and fewer numbers as this course progresses. It becomes letters, everything. So when I consider knowns, even if I know, like, even if you say, well, don't you know the mass and you know the spring constant K and you know the initial position is 0.15, Yeah, I know them in the sense that they're given and measurable, but I don't care what the actual numerical values are. In other words, I'm going to say known, what are known are M, K, and X naught. They're known in the sense that they can be treated as constant values throughout whatever math I'm about to do. They're not variables, but they're just letters as far as I'm concerned. Whatever I solve for here, I want to be true whether the X naught happens to be 0.15 or 0.17 or whatever. So I know these two things. I can put them to, and I know the only force acting, sorry, I also know the only force acting on the mass is a spring force. Okay, so I know so I can say, I'm gonna go to the next page, since F equals negative KX, and since this is this, and since only one F, like since that's the free body dog, in other words, I'm saying that this is true, right? I have this. Now remember, I'm looking for an equation that relates X to T. I'm getting somewhere because I have an X here. That's good progress, but I bless you, but I don't have, sorry, but I don't, so I have an X is a variable. That's good, but I don't have, sorry, but I don't have T on the other side. I have this other variable A that is related to T. Okay, so I think I'm gonna make a substitution. How is A related to T? Well, let me be very careful. I know that average acceleration from old physics, I might know that this is true. The average acceleration between any 2 points is the change in velocity between those 2 points. That is true, but that's gonna get me into trouble because the average is changing all the time here because the instantaneous is changing all the time. So a better way to make use of all of the knowledge that I was like churning about in the last few parts is, even though average acceleration equals that, this statement that I wrote down here is not referring to average acceleration. It's referring to instantaneous acceleration. And what I know is that instantaneous acceleration, by definition, instantaneous acceleration, is defined to be the second derivative of position with respect to time, right? It's the derivative of the derivative of position with respect to time. So that, and that's a triple equal sign, like that's the definition of A. Oh, and I know it's 1:30. Let me just write this. So this fast thing is you're not gonna have new, no. I'll say it's one more, you're not gonna have new homework. I'm gonna take 1 more minute to just write this down. I should assign you to look at the next video, and if you really want to, please do, but I'm not even saying that because I wanna catch up to myself and I feel bad. And don't worry, we will not fall behind the material, we won't. But I'm gonna say there's not new homework due Thursday. Just bear with me for one more line. We'll plow through all the rest of this on Thursday, and then we'll be in a better position for me to give you, I just don't wanna waste, if you wanna look at the next video, you can. But the line I'm going to do for right now is just this. I'm going to substitute in and say, okay, and I know it's 1:30, as I said, and I know, well, anyway, I'm going to sub in and say this. Oh, wait, I'm going to leave it at that for the moment. I'm going to say what we have here. I'm going to leave this for the moment and say, look, now, in a way, the good news is we've done the hard part. We have an equation now that has 2 variables in it, X and T, and everything else in there are not variables. So that's good. In a way, we just did our job. We got X related to T. However, as you can see, we don't really have X as a function of T. We have the second derivative of X with relation to T is somehow related to X. Like, this is not done. We're not finished. We have to unpack this in order to get X as a direct function of T. I'm going to change something I just said. I apologize. I am going to post one sheet for you called Mathematical Methods, because we are ready for that sheet now. I'm going to post one homework in a couple minutes called Mathematical Methods. I'm trying to think if I believe you could do the whole thing for Thursday. But if you have to make choices, there's parts of that sheet are about derivatives and stuff, and parts are about vectors. The part that's relevant right now is the stuff about derivatives and integrals. So I'll even say that. I will post a sheet called Mathematical Methods, or it's called Math something. I'll post that momentarily after class. It will be due Thursday. But but there are parts of that sheet that are about vectors. You don't have to do those yet if you don't want. You could just turn in all the stuff about derivatives and integrals. You'll see the difference when you get there. It's obvious. I just can't remember which is first. So we're going to leave this here for now. I'm going to sign the math method sheet. We'll get right back to this step on Thursday. I know a couple people had to ask something quick right across class. So I'm going to hang out for 1 second, and then I'll eventually come up with an office hours. Sorry to rush again, always like this. But yes, if you need to ask a question, please stay. Other than that, I will please go to lab or whatever, community hour or whatever, and I will see you soon. But I'm hanging out because someone had to ask a question. So bye. Okay, hello. So I know at least one person here wanted. So hi guys. If any, so why don't we do this? If people don't mind staying for a couple people have to ask something that's like actually private. So I'd like them to ask it last, so to speak, or I'd like to have everybody else to be before that. So does anybody want to add? I don't mean that to be rude. Okay, but if any of you wants to ask a physics question first, before, like any of you who are right here now, like Stephen or Brianna or or Lloyd, like if you want to ask a physics, you certainly can. Or any, hello, or wait, you can hear me though, right?
Yeah.
Okay, so right, because you right. Okay, so like Brianna or Isadora or are you guys just hanging to hang, or do you have a physics question or or if it's a, how could I do this? I'm happy to answer any private question to any three of you, but if that's what it is, then why don't we? Actually, yeah. Wait. So Stephen, a question or Isadora there? Are you there? Hello. Or Brianna, hello. Lloyd, hello. Okay, Brandon, do you want to? It seems like no. Do you want to ask quickly, or do you want to put it in the chat and I can look?
I mean, it's not really like private. It's just more or less like this is the first time I'm actually like joining the class because I had not received an email like about the code or anything.
I'm so sorry.
So I'm behind on stuff.
I'm so sorry. Okay, got you. Right, and right. Okay. Wow. Yeah. All right. So let me back. So the first, and thank you for telling me. Sorry to be weird. The first thing I can assure you, especially because I believe, like, we will catch you up. Like you will. It will be fine as long as there won't be a problem. But thank you for telling me. So let me start with. Do you have the Google Classroom code for this?
Yeah, I think I just joined like 2 days ago when someone sent it.
Oh, okay, great. So the good news is like that, and you know, there's two different. There's one for this part, and there's one separate one for lab. Are you? Do you know that?
Yeah, I have both. Yeah.
Okay, great. All right. So as far as this part, I mean, the good news is, well, the really good news is, as far as any, like the syllabus is in there in the Google Classroom materials, and any work. There's luckily I've only actually assigned one homework so far, and it's the one that I'm in the process of going over right now. But wait, that's a slight lie. I'll correct that in a second. But like the homework that we're talking about right now, as long as you can actually find it in your Google Classroom, find the assignment or whatever, you can still absolutely hand this in, and you can absolutely hand it in for full credit. And that's even if you can even write down a bunch of stuff that you've gotten from these class lectures. That's okay. So you're not behind in terms of your grade. You're still in absolutely perfect position to get full credit for everything. One little thing that you might have missed, like, are you actually looking? Can you access the Google Classroom thing right now while we're talking? Can you see it?
Yeah. Let me just open my laptop real quick.
Okay.
All right, I'm on Google Classroom right now.
Oh, great. And do you have? And in fact, as long as do you have a couple minutes to go through something with, like, if you could spend like 3 more minutes with me, we could probably straighten everything out. Are you free right now?
No problem. Yeah.
Okay, cool. All right. So if you look there, I believe there's one assignment that came to your email or whatever. There's one assignment called HW trial number 1 or something like that. Like,
Yeah.
okay. So if you click on that, this would be a perfect, that was the first assignment that we did
Oh,
together.
I did that yesterday. Yeah. Sorry.
Great.
I saw it yesterday. So.
Oh, okay. And so if you did, and that was just to absolutely, and so I can look at yours right now. That, and the whole purpose of that is just to make sure that like you knew how to get stuff to me from here on in. Because as long as that worked, I'm going to check it right now, and I'll get, as long as I can give you a 50 for, like a 50 out of 50 for that right now, which is the goal, then we'll both know like how the whole thing works. In other words, then as long as you get a 50 from me in 2 moments for that, then you'll just do the same type of thing for this thing on a spring homework. Like just write out all the, on a separate sheets of paper, write out all your work, and you know, show all work, but like for each question, make sure what question you're on is clear, write down all the work, box your final answer. And no matter how many pages it is, just like scan it all together into one big PDF and submit for, in other words, and you'll get full credit for that as well. Like it doesn't matter. You're definitely not late or something, as long as we both know how to do this. So wait, let me just see it. Make sure you did the first. Okay, cool. And then it'll proceed like that. Like, oh, and as far as, well, okay, sorry, I'm getting ahead of myself. Let me just do this, make sure we're good. I should, all right, it's coming, it's coming. Okay, hold on, I'm finding it. Brandon. Brandon. Okay, so I see yours. Let's see. All right. Okay, so I'm looking. Right, perfect. Right. So you gave me a 2-page PDF for the first thing, and that's exactly what I wanted. I just wanted to make sure that, because for some people it's a big deal to compile a bunch of photographs together into one multi-page document, but obviously you know exactly how to do that. So, so in 1 second you should see. Okay, so in 1 second you should tell me if you.
Yeah, I got a message.
Great, and it should clearly say 50 somewhere, like your grade should be clear on it somewhere. Or,
yeah, 50 out of 50. Okay,
great.
I got it.
All right. So we'll do, so that exact same interchange is what you'll do for that other homework that we were just, and again, it's totally fine if you do any of the questions from what we did in class. I don't care, you know, just show what you're doing. And on the very last question, since we have a long way to go to solve it, there, if you want to show me a bunch of work just to, you know, show that you're caught up to, you know, I don't expect you to, you don't necessarily, you couldn't get the right answer to the last one without looking up a bunch of stuff on the web, and you are allowed to do that, but you don't have to. Yeah, so because I guess the one, you will always get full credit for trying. That's the point of the homework, and you definitely can do it with other people, and you can definitely use any resources, blah, 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 blah. Like as long as you do it and turn it in, you get tons of points. That's a lot of what I spent time explaining on the first day, is that you just, all homework in effect works like extra credit in the end. Like you just get points for doing it, right or wrong. And and any question you skip or something, you don't get those points, but all the points at the end then get divided by one number. Like they get scaled down by a multiplier, but then, which is the same multiplier for all students, and then all those homework points that got scaled down get added to your actual exam average at the end, to give you a final grade average. And you know, it can be, often people get anywhere from like 9 to 12 to 14 points added to their average from sheer homework. Just to, I'm sorry, maybe you know all this, but anyway, you're not behind. There's only been that one homework. You can totally still turn it in. And as far as the materials, there's one last quick thing. You probably know this too. I'll just say this before I forget. The one last thing, oh no, I guess I put in the stream, is that link to the YouTube channel that has all the, like every one of these lectures I will post at night, like today's like, right. But, and they'll all be posted to this YouTube channel. But the truth is that all of the lectures for the exact version of this course from last summer like are already there. So you are welcome in a playlist. So you're welcome and encouraged. So you can watch anything and like, I'm not trying to hold you in suspense on the material, if that makes sense. And
Yeah.
should I give you that link, or do you have that link somewhere? I don't know if I.
It's the jjphysics.com, right? The
Oh, right.
Yaverbaum?
Yeah, exactly.
Okay, yeah,
Exactly.
it's here. Okay.
Okay. So yeah, so thank you for, I'm very sorry that the communication was bad. My communication's always bad. I mean, I'm totally
That's
sorry.
perfectly fine.
Okay, well, I appreciate it. All right. And just remind me, you are a John J,
Yeah, I'm a John Jay student. Yeah.
and
I
wait,
took
and you
physics
took,
last semester.
right, with me. I mean,
Yeah.
okay, I thought so. And that's why I'm sorry when I saw your name, it seemed so familiar. I didn't even know there was an issue. I thought we were just like, I didn't realize you'd missed it. All right. But so you know all this and you know me and you know you'll be fine.
Yeah.
Okay. All right. Cool. Awesome. All right. So I'm good if you're good then.
Yeah, I'm good. I just wanted to make
Great.
sure that I was on.
You're totally.
That was good.
Yeah, you're perfect. And I appreciate your spending this time. All right. So thank you so much. And Lloyd and Isadora, if you're not there, I'm going once, going twice. Lloyd or Isadora, there. All right. Well, bye all of you then. Bye, Brandon.
Okay.
It's been a pleasure.
Bye.
Okay. Bye.
Thank you.